in this lesson, we're going to look a little deeper at some of the things we're doing with these exponential functions. So the first question, and I made this lesson with some guiding questions, what does Newton's law of cooling look like when graphed? So we learned about Newton's law of cooling in the last lesson, and to show this, we're going to look at two pretty similar situations with only one difference. So the first part says a cup of coffee is poured from a pot. Its initial temperature is 180 degrees Fahrenheit. And K is 0.2337 per time in minutes. This cup is left sitting in the room that is 75. So I have Newton's law of cooling down here. We're just going to write down the values that we know. So the temperature surrounding the object, the temperature of the room is 75. The initial temperature is 180. T is a variable, small t, and this specifically we'll need to cross out. This is minutes, and we know we can change that time value depending. So this will be minutes as well. The temperature of the object after t minutes, so that big T is going to be our A of t in this case, and then the decay constant is 0.2337. So we're going to plug those values in to the formula that's up here. So the surrounding temperature is 75. Then we have 180 minus 75 for T sub 0 minus T sub alpha. We have our base is E to the negative 0.2337 T. Looking at our second situation, we have another cup of coffee starting at 180, the same K value because it's a cup of coffee. But this cup is brought outside where it's 42 degrees Fahrenheit. So the only thing that's going to change this time is that in B of t, we're going to have 42 for the temperature surrounding the object. So that parameter will change in the function. So 42 is where the 75s were. So those are my two functions. Now, in order to keep the video a decent length, I have some of the stuff already done in the calculator. So if you need to get caught up on your calculator, you can pause that. So I took both of my functions because we're going to graph A of t and B of t on a grid. And they should already be in y equals. So if you need to pause and take those in, make sure you're using x instead of t because that's what we have in our y-x plane. And I'm going to scroll down here to get a little more information. So a nice thing about this problem is they gave me my window. So right now, if I took my graphs and pressed zoom 6, I would see nothing. And that's because this only goes up to 10, for example, in the temperature direction and the y direction. And we know we're up at 180. If we think about it, these cups of coffee are never going to be 10 degrees because they're not out in the freezing cold. So I'm going to go to window, and looking at my scale, my x goes from 0 to 25. And we haven't used this too much, but this x SCL that's below the min and max, that's a scale. So I'm actually going to set it with the 5 that's in my table to make that, or in my graph to make that even better. My y is from 0 to 200. And my y scale looks like it's by 40s. I could use by 20s because each grid line is 20, but I'm going to use the 40s. So now I'm going to press graph. And I see my blue line is A of t, my red line is B of t. Now to get points, I'm not going to require you to draw a table, but I'm going to draw a table just to show how that would work. When I go to my table, I have a whole lot of points here. So I already fixed mine. Do you see how my table goes by 5s? I'm going to show you how to do that. So if you go to second window, which is second table set, I started my table at 0. And I made delta table, which means the change in the table go by 5. So yours is probably a 1 here right now, and I made it to a 5. And that's why if I look at my x's, they go by 5s. So I am going to copy down this table and then graph the points. I can make a table with both values just like I see on the calculator. So I'm going to have t, A of t is my y1, and B of t. So t is my x. And I'm going to move a little bit on the directions there. So A of t values, I'm going to round to the nearest whole number. And you kind of have some liberty when you make a table. Really, how accurate can I be on this graph? So whole numbers are fine. I don't really need the decimals. Although I am on this last one to be able to talk about it, I'm gonna round that one to the nearest 10th. And my B of t values, I have 180, so we see they have the same start value, which we'll talk about why that makes sense in a second. 85, 55, 46, 43, and 42.4. So once again, I rounded these to the nearest 10th, and we'll talk about that when we answer the end behavior question. So I'm going to graph, first off, try to do the same colors. So my blue graph is my A of t. And I have 180. At 5, I have 108. And at 10, I have 85. 15 is 78. And then we have 76. And it's really hard to get these, perfect, but about there. Okay. So here is my A of t graph. And my B of t graph starts at the same place, but we see it pretty dramatically decreases and it breaks away from a blue graph. It comes down to 55 here, and 46, and 43. So 46 should probably be a little lower there, 43, and 42.4. So the next question says, describe how the end behavior of the graph makes sense for the situation described. And specifically, the left end behavior, like this side over here, if we talked about that end behavior, we're talking about negative time, which doesn't really have any purpose for this graph. So really, I'm talking about the end behavior on the right side. So when I look over here and at these arrows over here, I should notice first off, for A of t, and actually I'm going to write this differently. I'm just going to write as time goes to infinity, right? So we're assuming, some sort of infinite time for this cup of coffee because we're talking about behavior. My blue graph, A of t, so the y value for the A function is heading towards, and if I look in this table at my values, I see it's heading towards 75. At some point in my table, pretty soon it'll round it to 75. The bottom I see here is 75.001, but it's heading towards 75. And for B of t, I'm heading towards 42. Now, that should make sense when we look at our functions, okay? If I scroll up, and I think about my exponential function, I know my exponential function, when it's decreasing, right, from this negative value here, should be heading towards 0. Okay, so both of these should be heading towards 0, but this number, this plus 42 and this plus 75, our vertical shifts are moving the graph up that number. So instead of getting an asymptote at y equals 0, this red graph has an asymptote at 42, and this blue graph has an asymptote at 75. Now, for the situation, if you ask someone what happens to coffee if you put it in a room, well, the coffee is going to approach the temperature of the room. So when we say, why does it make sense for the situation described, we can write coffee, or really any substance, approaches the temperature of its surrounding. Now, just a little more that we're going to get into on the next page. One, it's pretty crazy that this thing that, things cooling down, heating up, which is a pretty, applicable thing in science, is exactly an exponential function. So we have linear functions, straight lines, and exponential functions, but in between them, we could draw all sorts of curves that have, less curve, more curve, and things cooling down or heating up when put into different surroundings always follow exactly this exponential curve, like Newton's law of cooling. The other thing that's interesting is that E is in the formula. Like, why does this have E in the formula? And we will talk a little bit more about that on the next page.